We made it to Chapter 3 on Building Science Basics. In this chapter, I'm going to explain some basic fundamentals of building science so that you can better understand why the recommendations I give for improvement options will actually work. This chapter is going to be more technical than others in the course, but I try to simplify the concepts you need to know so that they're easy for you to understand. Stick with me till the end and you'll probably have some aha moments before it's all over. I know you're excited to learn, so let's dive in. Let's explain the house as a system. Every house has multiple components that make it all work together as a system, and understanding how these components are related will help you understand why issues develop in your home. Heating and cooling systems, ductwork, water heating equipment and plumbing systems, exhaust fans and vents, windows, doors, and insulation are all part of the home system, and that's not all. When you change one aspect of your home, it's likely to affect other things as well. For example, air sealing holes in your house and adding more insulation should make you feel more comfortable, but it also lowers the heating and cooling load on your house, which can negatively affect the performance of your heating and cooling system. Why is that? Because a tighter house with better insulation requires less heating and cooling to keep it comfortable. So your heating and cooling system needs to run less in order to maintain your thermostat's set point temperature. Well, isn't that a good thing, running the HVAC system less? Not exactly. In the summertime, when it's hot and humid, you want your AC system to run for at least 20 minutes so it can reach its peak efficiency and remove more moisture from the air as it cools. After all, dehumidification is one of the primary roles of an AC system. So if your AC unit only runs for about 5 or 10 minutes, it will not be long enough to dehumidify the air, which leaves the inside of your house feeling stuffy or clammy in the summertime. The same thing goes for maintaining equal temperatures in each room of your house, in heating or cooling mode. Your HVAC system needs to run long enough to distribute the air to and from every room, and the rooms furthest away from your furnace will likely have the greatest temperature difference due to the duct leakage and heat loss that happens along the way. So what makes a house comfortable? Well, being comfortable is largely a subjective thing for each person, but in general there are 4 primary measures of a comfortable home. The 4 measures are: number 1, indoor air temperature; number 2, the relative humidity of the indoor air; number 3, the air distribution method of the heating and cooling system; and number 4, mean radiant temperature, or MRT. Let's talk about indoor air temperature. This is the temperature that you set your thermostat to that makes you feel comfortable at home. The thing is though, every thermostat is different and each one reads temperature and relative humidity a little bit differently. So one thermostat right next to another one in the same room could be off by 2 to 5 degrees. They're even worse when reading relative humidity, and they can be off by 5 to 10% or more. Here's another curveball for you. The temperature showing on your thermostat could simply be inaccurate, either showing you a temperature that's higher or lower than the actual air temperature. This is where it's useful to have a simple tool like an air temperature meter to be able to compare your thermostat reading to, and if you have more than one thermostat in your house, you should calibrate all the thermostats based on what your separate air temperature meter reads. Number 2, relative humidity of indoor air. This is the percentage of water vapor found in the air compared to the maximum amount possible at that same air temperature. Think of it this way. If the relative humidity of outdoor air is 100%, then it will be raining outside. The air can't hold any more moisture and it has to release it. Inside your home, the ideal relative humidity range is between 40 to 50% year-round. If it goes below 40%, your eyes, skin, mouth, and sinuses will become dry and irritated, which can lead to infections and other health problems. If the relative humidity goes over 60%, it creates conditions ripe for mold, mildew, and fungal growth inside your home, which can lead to serious health issues as well. This is why oversized heating and cooling systems cause so many health and comfort problems. They usually don't maintain even temperatures across the home, and as a result of short run times, relative humidity is often too high as well. Number 3, air distribution method. We just touched on this briefly when discussing maintaining even temperatures across the home, but this has everything to do with the duct system connected to your heating and cooling equipment and how it was designed for your house. A poorly designed duct system will not move enough air to and from the rooms as it should. We often find the return air side of the duct system is usually the problem, And specifically, the return drop and trunk line are too small for the amount of airflow needed by the heating and cooling system. A lot of times this happens because the original furnace or heat pump was replaced by a bigger unit at some point, which requires more airflow than the original ductwork was sized for. You might have a room in your house that gets really hot or really cold at different points in the year, and you may even notice if you open or close a door to that room that it significantly improves the comfort inside there. This is a sign of an unbalanced duct system, meaning that either too much air is going into that room or too much air is going out of that room, and this happens for a variety of reasons. The three most common reasons this happens are due to 1. Improperly sized ductwork, usually being too small. 2. Ductwork that's not sealed between the heating and cooling equipment indoors and the rooms that it serves. And 3. A lack of return air duct in bedrooms or an insufficient pathway for the air to leave those rooms. All of these reasons will be discussed in greater detail in Chapter 8 of this course. Let's discuss number 4, mean radiant temperature, or MRT. MRT is defined as a measure of the average temperature of the surfaces that surround a particular object. That sounds technical, right? Stay with me here and let's use the following example. You're sitting on the couch in your living room, which has several windows, a door, walls, a floor, and a ceiling. Your thermostat is set to 70 degrees. Let's say it's 30 degrees outdoors and the surface of your exterior walls are 65 degrees, your ceiling is 70 degrees, and your windows and door surfaces are 55 degrees. Now, without getting overly complicated here, just understand that if the windows have more surface area than the exterior walls, then the 55-degree surface area of the windows will lower the MRT and you will feel less comfortable. So the main idea here is you want to avoid having surfaces in a room that are much warmer or colder than the thermostat setting that you want. Otherwise, you're going to be uncomfortable. Now let's discuss thermodynamics, or how heat transfers. Okay, by now you might be thinking, I'm not an engineer and I don't need to know all this stuff. But stay with me because a general understanding of thermodynamics and how heat transfers will greatly help you understand why the improvements we recommend will work. The main things you need to know here are warm air rises but heat transfers in all directions. Heat moves from hot areas and surfaces to cold areas and surfaces. Moisture moves from wet areas to dry areas. And air moves from high pressure areas to low pressure areas. There are also 3 methods of heat transfer, and they are the following. 1. Conduction, by 2 or more materials physically touching each other. 2. Convection, by air or water moving across or through something. And 3. Radiation, typically from the sun's rays hitting a surface. An example of conductive heat transfer would be your hand touching a hot stove and getting burnt, or touching an ice cube that makes your hand cold and slowly melts the ice. An example of convective heat transfer would be cold air blowing on your body in the summertime to cool you down, or a fire inside your house warming the air indoors in the wintertime. An easy example of radiative heat transfer is when your car is left outside in direct sunlight, which causes the metal to get hot and the air inside the car as well. So what is R value for insulation? The Owens Corning Company and their Pink Panther mascot have told everyone for decades that higher R value equals better insulation, but that doesn't tell the whole story. R value is basically the ability of a material to reduce heat transfer through it, and it only accounts for conduction, not radiation and not convection. So why does this matter? Because when hot or cold air moves through an insulation material, which is convection, it reduces the effective R value of that insulation. And most homes today have porous insulation in them like fiberglass and cellulose that air can move through easily. This is why simply adding more insulation to your attic before air sealing the holes and penetrations through the ceiling and the top plates of your walls will not be as beneficial as air sealing first and then adding insulation. To summarize this, the higher the R value is for insulation, the higher the resistance it has to conductive heat transfer only. We're going to talk all about insulation in greater detail in Chapter 6. What is a U factor for windows? The main thing to know here is that U factor is just another way of showing the ability to reduce heat transfer through materials And this is typically only seen in window and door performance ratings. U factor is calculated by dividing 1 by the R value of a given material or assembly. So for windows, that includes the glass panes, the frame, and any air or gas between the panes. So for example, most windows have an R value of R3 to R4. So to calculate their U factor, you just take 1 over R3 or 1 over R4, which equals 0.33 and 0.25 respectively. With U factors, the lower the number, the better the resistance to heat transfer. If you have a relatively modern house built in the last 40 years with double pane vinyl framed windows, the U factor is likely between 0.30 and 0.45. All that said, it's more important that windows be airtight than have a really low U factor, because there's no point in having efficient windows or doors if they still leak air. Now let's discuss thermal boundaries in houses. If you haven't fallen asleep yet, here's where science meets practicality in your house. Every building that's heated and cooled has what's called a thermal boundary and a pressure boundary. And essentially your thermal boundary consists of the insulation and building materials that make up the exterior walls, floors, and ceiling of your home. An easy way to remember what a thermal boundary is when you put on a sweatshirt in cold weather to keep your body warm. The sweatshirt itself is your body's thermal boundary, and if it doesn't completely cover your body, the parts that are exposed or uninsulated will obviously be colder. Now let's discuss air movement and pressure. We just described what a thermal boundary is, and now we'll discuss another important layer to that called the pressure boundary. The pressure boundary is what keeps the air inside your home and separates it from the outdoors. Any air that leaks in and out of your house goes through the pressure boundary one way or another. Think of the pressure boundary like a blown up balloon, and the thermal boundary is like a blanket wrapped around that balloon. If you were to poke holes in the balloon by sticking a needle through the blanket and into the balloon, which is the pressure boundary, air would leak quickly out of it, but the blanket, which is the thermal boundary, would still be intact. The problem now is that you would have to constantly blow air into the balloon to keep it inflated, which may not even be possible since there are holes in it. And this is essentially what your heating and cooling system has to do all day and night when you have a leaky house. When you air seal a house properly, you are effectively air sealing the pressure boundary. You'll learn all about where and how to air seal your house in Chapter 5 of this course. Now let's move on to air movement. Air movement in buildings is driven primarily by 4 things. 1 being stack effect, 2 is wind, 3 is temperature differences between indoors and outdoors, and number 4 is HVAC system ductwork. I'll expand more on each of these things now. Number 1, stack effect. The term stack effect or chimney effect is the movement of air into and out of buildings through unsealed gaps and holes in the top and bottom of the building, which results from air buoyancy. There are 2 main things to remember here. Buoyancy of the air increases as the air temperature rises, and the taller a building is, the greater the stack effect will be. You've probably heard the term heat rises before, and it is partially true, but it's more accurate to say that hot air rises because heat actually transfers in all directions. So what happens naturally in taller buildings is air is drawn into the bottom of the building through unsealed gaps and cracks, and the warm air inside rises up through the building and exits through leaks at the top of the building. The same amount of air that is drawn in at the bottom of the building will also leak out at the top. This is why it's so important to air seal any holes you have at the top and the bottom of your home first. Now let's discuss wind. This is pretty self-explanatory, but the stronger the wind is blowing on your house, the more air will be drawn into it and leak out of it. Think of it this way. When you have a leaky house and it's windy, that wind drives convective heat loss in the wintertime and heat gain in the summertime, which forces your heating and cooling system to run longer to keep you comfortable inside. Strong winds will also bring in dust, sand, pollen, moisture, and other pollutants nearby, so if you have allergies or health issues, you really need to pay attention here. Let's discuss temperature differences. Air leakage in buildings increases between indoors and outdoors as the temperature between indoors and outdoors increases. That difference in temperature is referred to as delta T. The greatest temperature difference between indoors and outdoors, and therefore air leakage, will occur in the wintertime. And that cold air coming into your house will also be very dry, making you even more uncomfortable. This is why humidifiers are often needed in leaky homes in the wintertime, in order to feel comfortable and even to stop nosebleeds and sinus infections. HVAC duct systems. Air leakage driven by your duct system is usually an issue only when you have ductwork located in an attic, a ventilated crawl space, or in a garage. The reason why ductwork can drive more air leakage in your house is because most duct systems are not air sealed properly at their connections. And when those connections are located outside the house, then air from the supply side of the ductwork will leak out of the house, and the return side of the ductwork will suck air into the ductwork and into your house from wherever it's located, in the attic, the crawl space, or the garage. And this is gross. Leaky ductwork located outside the living space is a big reason why people experience dusty homes, have indoor allergy problems, and it can also make the air inside your home more humid in the summer and dry in the wintertime. Not only that, it can significantly increase your utility costs. You'll learn more about HVAC systems in Chapter 7 and duct systems in Chapter 8. Now let's discuss controlling water indoors and outdoors. Before you begin any home improvement that involves air sealing or adding insulation, you must be sure that you don't have a moisture problem inside or around the outside of your house first. If you do have a moisture problem that goes undetected and you air seal and add insulation to your house, you could actually end up making the problem worse. Leaky homes have one benefit when there's an active moisture issue present. They dry out more quickly because of the extra air movement through them. But we don't want leaky houses in the first place, and nor do we want water intrusion anywhere near our home. So it's best to address the sources of any moisture issues first. Bulk water versus water vapor. The two primary methods water enters your home are by bulk water and water vapor. Bulk water is essentially rainwater that accumulates around the perimeter of your house, and if you don't have proper grading where the ground slopes away from your house, then it's more likely that the rainwater will drain into the ground surrounding your house. If your foundation walls are regularly in direct contact with wet soil, the concrete or masonry materials will absorb that moisture over time. Remember, wet goes to dry, and moisture eventually transfers into your basement, cellar, or crawl space, which is the dry side. That wet ground outdoors really can affect the relative humidity of the air inside your home. Fixing any grading issues is the first step in fixing bulk water problems. Gutters and downspouts, along with extensions at the bottom of the downspouts, are used to direct rainwater away from the foundation of your home. So if you live in an area that rains often, it's really important that they be free of debris and able to move rainwater away easily, at least 5 feet away from your house, and 10 feet or more is preferred. If you have a crawl space or a cellar, it's very important to install a vapor barrier over the entire dirt or gravel floor to prevent water from evaporating up into the house. A 6 mil thick vapor barrier is the minimum thickness you need over the ground, and the seams should be overlapped 6 to 12 inches and taped with a vapor barrier tape, not duct tape. 10 to 20 mil thick vapor barriers are more than enough for the vast majority of homes, and anything more than that is overkill and likely overpriced. The perimeter of the vapor barrier should be sealed to the interior of the foundation walls, ideally with closed cell spray foam insulation. But a combination of foam board and spray foam insulation or other waterproof sealants also works well too. Water vapor is moisture held within the air, and as a rule, warmer air can hold more water vapor than cold air can. This is why in the summertime, the warm outdoor air is more humid than the cooler air inside your house. And in the wintertime, the warm indoor air is more humid than the colder outdoor air. Relative humidity is basically the amount of humidity or moisture inside the air as a percentage of the maximum amount that air temperature can hold. This may sound a bit confusing, but the bottom line here is you want the relative humidity inside your home to be between 40 to 50% year-round for optimal health and comfort. So properly controlling the moisture you create inside your home is very important. The main way you control moisture indoors is by using exhaust fans when you shower or cook food, and especially when boiling food. Exhaust fans should be running the whole time you shower or cook. Otherwise, the drywall and the wood components of your home will absorb the water vapor that's created, and that'll keep the relative humidity inside your house higher than you want. The secondary way you control moisture indoors is with your AC system. As the AC system runs, it removes moisture from the air. So it's important that your AC system runs for at least 20 minutes before shutting off in order to dehumidify the air properly. This is why oversized AC systems are such a problem in humid climates. They never run long enough to dehumidify the air, which leaves the indoor air cold, clammy, and uncomfortable. Installing a whole house dehumidifier or a portable dehumidifier in your home will help control moisture that enters it, but you still need to address the sources of the moisture first. Otherwise, these are just acting as band-aids without fixing the underlying issues. Now let's discuss solar orientation and shading. An important yet often overlooked aspect of a home's performance and ability to maintain a comfortable environment indoors has to do with how much sun directly hits the house, and particularly the windows and glass doors, which allows heat and light inside. In the United States, we're located in the northern hemisphere of Earth, and so the greatest amount of sunlight naturally comes from the south, which is where the equator is in relation to the US. If your house has a lot of windows facing south and there are no trees, roof overhangs, or buildings nearby to provide shading for the windows, then your house will get hotter than you'd like to in the summertime and cause your AC system to run more to cool the house down. This also increases the cooling load on your house, which requires a bigger AC equipment to cool your house down. Adding trees, extending roof overhangs, and adding window awnings on the outside are the most effective ways at stopping the sun's rays from hitting your house in the first place, but it's not always feasible. Some people add solar tinting to their windows to reduce the heat gain as well, but this can also void your window warranty, so use caution there. Using blinds and curtains will also help reduce the heat gain from the sun, but the best solution is to prevent the sun's rays from hitting your house and windows in the first place if it's possible. All these things help reduce the cooling load on your house, which reduces the size of the AC equipment needed and saves electricity costs as well. Conversely, in the wintertime, you actually want the sun to hit your house to help warm it up. So open up any blinds and curtains covering south-facing windows in the wintertime to get some free heat inside. This helps reduce the heating load on your house and therefore reduces the size of the equipment that you need to be comfortable. That's it for the Building Science Basics chapter. In the next chapter, we'll discuss the most common foundation types out there and the pros and cons associated with each one. So I'll see you there soon.